Okay, this video is going to cover part 2 of chapter 8, section 6, which is probability. A quick recap of what we talked about yesterday. One of the biggest differences and what you need to pay attention to in the language of your questions is if the probability is an or statement or an and statement. So if it says you want this or that, or you want to get this and that, or both things, or neither things, those last three, the and, obviously the both, the neither would be and statements. And if you said this or that, then this is your or statement. If it's an or statement, then you have to find out if they are mutually exclusive or they are not mutually exclusive. Mutually exclusive means that they can't be the same thing. So you can't have an even number and an odd number, or something less than 2 and greater than 7. Those would be mutually exclusive. A red card and a club. Those would be mutually exclusive. So you do the probability of the first plus the probability of the second in that case. If they are mutually exclusive, or not mutually exclusive, that means that they can overlap. So a red card and a heart, or an under 3 and even, those can be both. And when you do that, you would do the probability of the first plus the probability of the second minus the probability of the overlap. So A overlapped with B. Then we talked about and statements. And statements, again, if it's both, neither, this and this, are going to occur in multiple events, like 1, 2 pulls of something, or 3 pulls, or 3 rollings of the dice, that kind of thing. And for and, you have to determine if they're independent or if they're dependent. And if they're independent, it means one does not impact the other. So this would be a randomly generated number. This would be a roll of the die, a flip of the coin, or something with replacement. You took it out, but you put it back. And for those, we do the probability of the first times the probability of the second. And then your and statements that are dependent, so you altered the set in some way. Somebody goes up and grabs a box out of a rock out of a box, but doesn't put it back. Or they grab a sock from a drawer and doesn't put it back. Then they're dependent. And so we do the probability of the first times the probability of the second, given the first has already occurred. Second. Given the first has already occurred. And you always assume you got what you want the first time. So if you wanted to get 2 red rocks, we assume we got both red, or you got the red the first time. If you wanted to get a red and then a green, you assume you got the red the first time. All right, so let's get into some examples. This says, tell whether the events are independent or dependent. A box contains yellow and brown dog treats. You randomly choose one dog treat from the box. You do not replace it. Then you would choose another dog treat. And event A, the first dog treat you choose is yellow. Second is that it's brown. So we're not actually finding the probability here. We just want to know if these are independent or dependent. And the wording that's super important is you do not replace it. You do not replace it means that these are dependent. After that first pull, you have altered your sample space. B, a jar contains red and blue marbles. You randomly choose a marble from the jar and then replace it. Then you choose the second one. So the first marble you want is red, second is blue. And what we're looking at here is, are you starting with the same set the second time? The answer is yes. So these are independent. Example 7, you spin the spinner shown, which is divided into 8 equal parts. Find the probability that you get a red on your first spin and a blue on your second spin. So this is not like a digital timer or spinner in which you can remove what you landed on the first time. This is a true timer, like a game piece. And so you spin the first time and you spin the second time, you're spinning the same spinners. So this is an independent. It's an and statement, so that's why I know to check for independent or dependent. And so I want probability of getting a red the first time times the probability of getting blue the second time. There are 1, 2, 3 spaces that are red out of the 8 total, so 3 out of 8, times there are 1, 2 spaces that are blue, so 2 eighths. I can either multiply across and then simplify, or I can cross cancel here. 2 goes in 8 4 times, and I get 3 out of 32. Example 8, a bowl contains 36 green grapes and 14 purple grapes. You randomly choose a grape, eat it, and then randomly choose another grape. Find the probability that both events A and B will occur. The first one is green and the second one is green. So let's talk about the sample space. It contains the grapes. At the beginning, you randomly choose a grape and you eat it. We are assuming you do not then put it back. So this means that this is an and, first of all. A and B will occur. So it's an and statement, and it is dependent. So if the first round has 36 green grapes over the total number of grapes, 36 plus 14 is 50. And I would multiply that by, I assume I got that first grape to be green, which means the greens have reduced 1, making this 35. And there's one less grape, which means this is 49. So I'm going to simplify this. I could do 18 and 25 to make those numbers smaller. And then 5 goes into both of these, 5 and 7. And multiply straight across. Actually, 7 goes into 49 7 times. And now I get 18 over 35. All right, example 9. Again, tell whether the situation is independent or dependent, then answer the question. Number 1, a drawer contains 12 white socks and 8 black socks. You randomly choose one sock and you do not replace it. So do not replace it means these are dependent. Then you randomly choose another sock. What's the probability that both socks chosen are white? So this is like saying the first one you want to be white and the second one you want to be white. That's why it's an and statement. So first one, that it's white, there are 12 white socks out of a total of 20 socks. It's an and statement, so we multiply, but we assume we got the white sock the first time, so the number of white socks goes to 11, and the total number of socks in the drawer now goes to 19. So again, I can reduce. 4 goes into both these. This would be 3/5, and I'd get 33 over 19 times 5, 95. Number 2, suppose you flip a coin twice. What's the probability that you get tails on the first flip and tails on the second flip? This is an and. Again, now you're flipping a coin, which means these are independent. And probability you get tails on the first flip is 1/2. Probability tails on the second flip is also 1/2. So I get 1/4. Example 10, you randomly select 2 cards from a standard deck of 52 cards. What's the probability that the first card is not a heart and the second is a heart? If you A, replace the card first, B, don't. So A is independent and B is dependent. So if I want a not heart first and I want the second to be the heart, then not a heart would be the other 3 suits. So the heart is 13 out of my 52. And if I take that 52 and subtract it by 13, I get 39 out of 52. Multiply these together, and 13 goes into 52 4 times. And I get 39 over 208. Now, the second time, you do not replace the first card. So this is the probability of not heart times the probability of the heart given the not heart was selected the first time. So probability of not getting a heart is still 39 out of 52, or 3/4. We could reduce it if we wanted to there. And then the probability of getting a heart after not getting a heart, there are still the same amount of hearts that we begun with, which is 13. But you did pull a card out of the deck, which means my deck went down to 51. So this is times 13 over 51. 3 goes into 51 17 times, and I get 13 over 68. All right, the last concept in this section is called the complement of an event, and we use these. Sometimes it's easier to figure out there are less of what you don't want than what you actually want. So sometimes it's easier to find the complement of the event, which means we take the probability what we don't want and we subtract it from 1. This little a is read as a bar. Okay, and that means the complement. So if you're given the probability of an event and it wants the probability of a complement, you simply subtract it from 1. Here is an example. And this little guy on the right-hand side is going to be super helpful. So ideally, you learn how to draw this, because anytime you're rolling the dice and you're summing two terms or two numbers together, there's a pattern to the result. But you don't want to have to keep writing it out every time or figure it out every time. So if my first die has the options of 1, 2, 3, 4, 5, 6, and the second die has the options of 1, 2, 3, 4, 5, 6, I add those two together. 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4, 4 plus 1 is 5, 5 plus 1 is 6, 6 plus 1 is 7. Go to the next line and notice that this went up by 1. So we start at 3, then 4, then 5, then 6, then 7, then 8. Next line, we start one more. We start at 4, then 5, then 6, then 7, then 8, then 9. Next line, one more. 5, then 6, then 7, then 8, then 9, then 10. And then one more, 6, 7, 8, 9, 10, 11. And last up, one more, 7, 8, 9, 10, 11, 12. So it doesn't matter if you look at it going left to right or top to bottom. They all increase by 1 in both directions. That first one being a 2 in the top. So you have your diagonal of 3s, your diagonal of 4s, your diagonals of 5s, 6s, 7s, 8s, 9s, 10s, 11s, and the last one is your 12. So if you can duplicate this, like if on your test you take a minute to duplicate that when you get to a question that talks about the sum of two die, it will significantly help you when you get to this question. So A says the sum is not a 6. Well, it says, first of all, two-sided die are rolled. Find the probability of each event. The sum of those two sides are not 6. Well, if I look at this graph, that's 1, 2, 3, 4, 5. There are 5 times that it is 6. But I'd have to count all the other times that it's not 6. So the complement idea is, instead of looking at when it's not 6, look at when it's 6 and then subtract it from 1. So 1 minus the probability that it is 6, which was 1, 2, 3, 4, 5, out of 6 times 6, which is 36. So I get 36 out of 36 minus 5 out of 36, and that's 31 over 36, which is easier than counting all the other ones. B says the sum is less than or equal to 9. So I can either figure out all the times it is less than or equal to 9, which are all these guys, and count them all. Or I could do 1 minus the probability that they are greater than 9. Oh, it said less than or equal to. So even the 9s would have counted the first time. And that if I do it this way, 1 minus the probability that it's greater than 9, I'm only looking at 10s, 11s, and 12s, which is 6. So 1 minus 6 out of 36, and that can be reduced. 1 minus 1/6, 6 minus 1/6, which is 5/6. So you can count the long way, or you can use those complements to save you some time. Okay, last example. This one is table-based. So a lot of times with probability, you're going to get table information or word problem information. You're going to have to answer questions. The table shows the number of tropical cyclones that formed during the hurricane seasons from 1988 to 2004. Use the table to estimate A, the probability that a future tropical cyclone in the northern hemisphere is a hurricane. So we want it to be both a tropical cyclone in the northern hemisphere, and we want it to be a hurricane. So tropical cyclone in the northern hemisphere is this column here, and that is a hurricane is the 545. So 545 would be put over the sum of 199, 398, and 545. 199 plus 398 plus 545 is 1,142. These will usually be answered in decimal form or in a percent. If it's in decimal, it's 0.0477. If it was in percent, it'd be 47.7%. So I believe this question, you'll see it on your WebAssign as to what format it wants the answer in. B says the probability that the hurricane is in the northern hemisphere. So now we want it to be a hurricane, and we want it to be in the northern hemisphere. So it's still 545, but it's out of the total of hurricanes. So 545 plus 215, which is 760. And 545 divided by 760 is 0.717 or 71.7%. All right, that's it for the notes. Please use the submit your notes and use the remaining time to work on the 8.6 homework. Have a fantastic weekend. I will see you Monday.